Alrighty, lads and ladies, welcome back to Calc 1 Honors. Today we're going to pick up where we left off last week, which was we learned a little bit about trig derivatives. I want to kind of take you through one of those arguments, one of those special limits, and then we're going to cook up derivatives of other trig functions. So if you give me just 1 second, the screen share rocking and rolling. There we go. Real quick, I think, do I have this in here? Okay, is it down here? I think so. Yeah. All right. So we're going to refer back to this in a second. So let me pop. Actually, not it. Yeah. There's so many ways to show this, but the best one is a simple geometric argument. Yeah. Okay. That's where we'll go to. But first. This is Calc 1, section OH1. It's a lecture. Today's date is the 1st of February, 2021. And today, we're going to formally get into trig derivatives. Section 3.3. And we might talk a little bit about the chain rule. Section 3.4. And a little announcement. I did go ahead and set the exam 1 date. Exam 1 will be next Wednesday. Which is, I think, the 10th. Let's triple check this. Yeah, next Wednesday, 2/10. Those are all horrible. This one's good. Okay. Next Wednesday, 2/10/21 during class. I'll talk a little bit more about the proctoring mechanism. Remember, the way this is going to work, you'll need to have your webcam set up. For honor lock, you will also need to have your phone set up on your desk using Zoom, showing me your hands in your workspace. So I want to be able to see your hands in your paper, like what you're writing at any given time. And I'll be recording both of those for any reflection. I don't expect it'll be an issue with you guys, but just to be fair, because I have to do this in some of my other classes to keep them honest, I got to do it across the board. The study guide for exam 1 will be out this Wednesday. Which I guess is the 3rd. And due at the start of the test. And this will be just a collection of a few problems, right? Not a lot, 10, maybe 15 problems, where I ask you guys to write up full solutions and submit those solutions on Canvas. This does a few things. First, it gives you practice at like scanning and submitting work to Canvas, which is something you will need for the test. But more importantly, it lets me see your work before the test. So this is the absolute latest you can hand this in is at the start of the test. But really, I want you guys to hand it in before then. Like if you could hand it in on the Friday before the test, or even Monday before the test, then I can go in and look at your work and give you some feedback saying, oh, on the test, make sure you write this, in this way to get credit. Or on the test, I would have to take off a point here. Or on the test, this would be full credit, perfect job. Just so you're not surprised by like how I grade and the things that I'll be looking for. So please, the study guide, as soon as it's out, get working on it and submit your written work for the study guide as soon as you possibly can. That way I have time to get in and look at it and give you some feedback. The points come from the submission of the written work, right? The points for the study guide that you see in the syllabus, 25 points each, that's for submitting your written work. And it's not a correctness thing. I'm not going to take points away from those 25 for mistakes you make. It's just for completion. So as long as you submit the written work with an honest effort on every problem, then you'll get full credit. The purpose of the study guide, again, is so that I can look at your work and critique it and give you some feedback before the test. I think that's very important. Any questions about this sort of announcement-y stuff? Okay, then let's get rolling. Last time, we talked a little bit about the derivative of sine. So last time, we saw that if f of x is sine x, then f primed of x is lim h to 0 sine of x plus h minus the sine of x all over h, which shakes out to lim h to 0 cos h minus 1 over h times sine of x plus lim h to 0 sine h over h times cos of x. And I claimed that this was 0 and that this was 1. So let me call this now L2 and L1. I claimed that L1 is equal to 1 and that L2 is equal to 0, which proved, or which showed, that f primed of x here was equal to 0 times sine x plus 1 times cos of x, i.e. that the derivative of sine was cosine. And this was an important discovery, but it all hinged on these two limits. So today I want to carefully prove to you that those limits have the values I claimed they have. And not just like looking at a graph. This is an honors class, so I want to go through the proof. The proof is not too bad. I do have a proof. You saw me opening it there in Stack Exchange that you can read through on your own. There's actually several proofs there. I'll be going through one of those. The one that I like the most compares a few areas, and you're able to build an inequality based on inclusion of areas, meaning like one area is bigger than another if the one fits inside the other. And from that, we will get the sine h over h limit. We'll get L1. And then once I have L1, I'll be able to prove L2 to be 0, just using some trig identities in algebra. So hopefully we all remember this. If you need to see the steps between here and here again, we went through those last Friday. It involves expanding sine of x plus h using the sum formula for sine. So sine of x plus h is sine x cos h plus cos x sine h. Then we grouped some terms. It wasn't bad. Again, that's also in the book if you want to read it, but we went through it last time. So let's see if we can cook up these two special trig limits. Everybody with me so far? Questions or anything we want reminders on from last Friday before we move on? All right, real quick, you'll hear me refer back to these two limits as special trig limits. I'll refer to them a lot through the semester, actually. And the sine h over h and cos h minus 1 over h both as h goes to 0 are or what I will call special trig limits. They're special because we go through a fair amount of work to prove that they have the values they do, and because they really can't be cooked up any other way that's not logically dependent on later work. So we're going to prove that lim h to 0 sine h over h equals 1. And here it goes. So I'll use the variable theta because I'm going to be making a geometric argument. So sine theta over theta equals 1. This is what I'm actually going to prove. It's the thing on the right, but it's the same, right? It's just I'm using the letter theta instead of the letter h. Consider the unit circle. Pretend like that's a circle. All right. Consider the unit circle. Here's some angle theta. And what I'm going to do is I'm going to look at a few different triangles. Now, I'll make sure I don't mess this up. I'm going to remind myself. Where's the one that I like? This is the good one. Yeah. Okay. So we're going to look at a few triangles within the unit circle. Yeah. We're going to look at the big triangle here. We're going to look at the sector of the circle. And we're also going to look at the big triangle that extends outside the unit circle. So if I come back over here, I can draw the vertical up here. And I can draw the little guy here. Which one are we going to use? Use this guy, 1/2 x, right? 1/2 base times height. 1/2 sine x, that's the little guy. Okay, so that's 1/2 tangent x. Yeah, that's the easier one to use. Okay. Okay. And the area of a sector of a circle. So by doing this, created sort of 3 geometric objects whose relative sizes are fairly obvious from inclusion. What I mean by that here is I've got a small triangle in here which is this guy. I have the area of the sector of the circle, which I'm going to shade in orange. And then I've got the big triangle, which is, this guy out here. And I think we would agree that in terms of areas, that the small triangle has an area that is smaller than the area of the sector. Which has an area that is smaller than the big triangle. right? Because this guy fits inside of this guy. So the little triangle's area has to be smaller than the area of the sector because the little triangle fits entirely inside the sector. And the sector has to be smaller than the big triangle because the sector fits entirely inside the big triangle. Everybody agreed? Does anybody remember the area of a sector of a circle?
Isn't it theta times r?
I think it's very close to that. So if you're going to go all the way around the circle, then that's theta equals 2 pi, right? And so that should be equal to pi r squared. So it's going to be theta over 2 times r squared. Right, if you're looking at a circle of radius r. But what's the radius of the unit circle? It's 1, right? The area of the, or sorry, the radius of the unit circle is just 1. That's why we call it the unit circle. So the area of this sector here is just theta over 2. So here, the area of this sector is just theta over 2. Now, what about the area of the small triangle? Remember, the point up here on the unit circle is the point cos theta, comma, sine theta. So the area of the small triangle here is 1/2 base times height. The base is a radius. So this is 1/2 base times height. And this we said is less than, I'll write it all in, theta over 2 times r squared. And this guy is also 1/2 his base times his height. I'll figure him out separately, but all right, different bases and heights here. Maybe I'll call this small base, small height, whatever. So the small triangle's base is 1. The small triangle's height is the y value here, which is sine theta. So this is 1/2 times 1 times sine theta. Now inside here, r squared is 1, so this is just theta over 2. And on the right-hand side here, this big triangle, his base is also 1, so this is 1/2 times 1 times, what is the height of this big triangle? Anybody see it?
Would it be 2 times sine?
It's not necessarily, it looks like it might be double the height of the little guy, right? Looks pretty close to that, but it's not necessarily. It's the tangent of theta. The height over here is the tangent of theta, this height. There's a bunch of ways to see it. First, this big triangle here is similar to this little triangle here. So this over this has to equal this over this. Well, this over this is sine over cosine. So sine over cosine equals this height over 1. So here we'll say, I'll even write it in, sine theta over cos theta is equal to the height over 1 by similar triangles. So for my big triangle here, sine theta over cos theta is equal to that height over 1. That's because the big triangle is similar to the little triangle in here. And this little triangle in here is the normal triangle we use on the unit circle to define sine and cosine. Sine's the y value, cosine's the x value, right? Opposite over hypotenuse, adjacent over hypotenuse. So the big guy's similarity to that gives sine over cosine equals h over 1. So h here is tangent of theta. All right, and we might call this b1, h1, b2, h2 if we want to be careful to make sure we don't confuse ourselves because the triangles are different triangles. Multiply everything by 2, rewrite tangent as sine over cosine, and you get sine theta is less than or equal to theta is less than or equal to sine theta over cos theta. Now divide everything by sine theta. You get 1 is less than or equal to theta over sine theta is less than or equal to 1 over cos theta. So here, from this line to this line, I multiplied everything by 2. That gets rid of my 1/2. And I rewrote this tan theta as sine theta over cos theta. Then to go from this line to this line, I divided each term by sine theta. So sine theta by sine theta is 1. Theta divided by sine theta is just that. And sine theta over cos theta divided by sine theta is just 1 over cos theta. Sine theta is canceled. Now I'm going to take reciprocals everywhere. And that's going to flip over my inequalities. So I'll get 1 is greater than or equal to sine theta over cos theta is greater than or equal to cos theta itself. Here, the step here was divide by sine theta. And now you're ready to use the squeeze theorem. Remember the squeeze theorem? The policeman's theorem? That's why we teach that before this, because we need it here. We're going to be rigorous, and we should. You can rewrite this if you want in the direction you're used to seeing, which is like cos theta, is less than or equal to sine theta over theta is less than or equal to 1. Right, just flipping this, take this whole inequality and flip it over like that, you get this. So Billy's taller than Joey is taller than Sally means Sally's shorter than Joey is shorter than Billy. And now apply the squeeze theorem. As theta goes to 0. So I get lim theta to 0 cos theta well, this cos theta is continuous at 0. This is just cos of 0. Oops, sorry, cos of 0, which is 1. And of course, the limit as theta goes to 0 of the function on the right here, 1, is just 1. So by the squeeze theorem, theta goes to 0 of sine theta over theta has to be equal to 1 also. And that's the game. So that limit plus, I called it L2, right? L2 and L1. L1, this limit that we're looking at back here, really is 1. So that's the proof of our special trig limit, right? Sine x over x or sine h over h or sine theta over theta goes to 1 as that variable, whatever you call it, goes to 0. This is a special limit that we need to hold on to forever. There are some homework problems this week that will ask you to use this limit to cook up other limits. And one example of a thing like that is how I get L2. So from this, we can prove that L2, which was the limit as h goes to 0 of cosine of h minus 1 all over h is equal to 0. Here's the proof. Lim h to 0 cos h minus 1 over h is equal to itself when you multiply by 1. But the way in which I'm going to multiply by 1 is as cos h plus 1 over cos h plus 1, like this. And of course, we have to remember that the tops and bottom of these fractions are always in parentheses. That's just implied by the fraction bars. And then I FOIL out the top. It's a lot like multiplying by the conjugate. Up here, I'll get cos squared h plus cos h minus cos h. Those cancel, minus 1. And then downstairs, I'll have h times cos h plus 1. It's a consequence of the Pythagorean identity. Sine squared plus cos squared equals 1. If you subtract the 1 over, you'll get sine squared h plus cos squared h minus 1 equals 0. And I want cos squared h minus 1, so I'll subtract the sine squared over now. I'll get cos squared h minus 1 equals negative sine squared h. So this piece over here can be rewritten as lim h to 0 negative sine squared h over h times cos h plus 1. And then I'll regroup some terms. I'll regroup this as lim h to 0 negative sine h times sine h over h times 1 over cos h plus 1. And I can take the limit of each of these three pieces separately. This first piece becomes the sine of 0, right? When you send h to 0, this becomes sine of 0 or negative sine of 0. This piece right here becomes 1. That's the special trig limit that we just figured out. And this piece over here becomes 1 over the cosine of 0 plus 1. Now you guys tell me, what's negative sine of 0? What's the sine of 0? Getting a little nervous. So I've got some tricks for the unit circle. Yeah, it's 0. So this is 0 times 1 times 1 over the cosine of 0, which is 1, plus 1. So it's 0 times 1 times 1/2, which is 0. Some neat tricks. I just posted these for, where they go? I just posted these for my other Calc 1 class. I'll post them for you guys too. To help memorize the unit circle, there's something called the left hand trick that can be very useful. Like if I want to know halfway up my my left thing, then I'll have √2 over 2 for both of the pieces. So here are the links. I'll add these to your guys' review material as well if you want it. I'll do that after class so we don't burn class time on it. But yeah, sine of 0 is 0 and cosine of 0 is 1. So this piece is 1/2, this piece is 0, this is 1, so you get 0 times 1 times 1/2, which is 0. So this guy really is 0, as I claimed. And that's your other special trig limit that you need to remember. All right, but the limit, h goes to 0 or theta goes to 0, whatever variable you want to use. Cos h minus 1 all over h, that is 0. So these are your two sort of special trig limits. Gotta hold on to them. The fact that the derivative of sine is cosine is a consequence of this, right? That's what we've seen. So I'll hold here for anybody who wants to take a screenshot or needs a second to write things. And then I'm going to summarize what we have so far together with what we did last week. Good so far? So, you know the derivative of sine is cosine. d dx of sine x is indeed cos x. And a similar argument, really the same argument, like it involves all the same special trig limits, will show that d dx of cos x is negative sine x. And I told you guys both of these last week, and then we cooked up a few other derivatives using the quotient rule. Anybody remember the ones that we cooked up last week in addition to these two? So using these, we can find derivatives of secant x, tangent x, cosecant x and cotangent x, just by applying the quotient rule. I'll do one of these. I know we did at least one of secant or tangent last week. Cosecant I have in your homework as something for you guys to prove, following the same sort of pattern here. So I'll go ahead and cook up secant. So for example, ddx of secant x can be calculated as ddx of 1 over cos x, right? Because secant is 1 over cosine. This can be found using the quotient rule as the bottom times the derivative of the top. So that's cos x times the top primed, 1 primed, minus the top times the derivative of the bottom, all over the bottom squared. So cos x times 1 primed is cos x times 0 minus 1 times the derivative of cos x. The derivative of cos x is negative sine x. And all of this is being divided by cos squared x. So this is 0, cos x times 0 is 0, minus 1 times negative sine x, that's positive sine x, over cos squared x. And then I just choose to rewrite this as 1 over cos x times sine x over cos x, because I want to write this as nicely as I can. And I know that sine over cosine is tangent. I know that 1 over cosine is secant. So this is the same as secant x tangent x. So the derivative of secant is secant tangent. And this one needs to be saved forever in our brain, along with derivative of sine is cosine. Derivative of secant is secant tangent. The way I remember this one is that secant is the guy who shows up in his own derivative. The only one that does this. Well, secant and cosecant. Right, so secant shows up in his own derivative. Tangent would be next. I'll go ahead and do tangent. I'm going to leave cosecant to you because cosecant is in your homework. Are there any questions about what we did here? How I got this? It's fairly slick, right? Okay, so let's move on. We'll go ahead and cook up tangent for you. The derivative of tangent. We'll do it as an example, but again, it's something you need to remember forever. Well, ddx of tangent x is the same as ddx of sine x over cos x, which by the quotient rule should be the bottom times the derivative of the top minus minus the top times the derivative of the bottom all over the square of the bottom. Now I just plug in the pieces. This is cosine times the derivative of sine, which is cos x times cos x minus sine x times the derivative of cos x, which is negative sine x. And all of that is being divided by cos squared x. And if we clean up the numerator just a little bit more, we'll see that this is cos squared x minus negative sine squared x, which is plus sine squared x, all divided by cos squared x. And a question I like to ask my non-honor students is, can I cancel these? Can I cancel the cos squareds? The answer there, of course, is no, right? Because cos squared is not a factor of the top. In order to cancel with this guy, I would have to factor this guy out. But sine squared doesn't have a cos squared that I can factor out. But there is something I can use. I know that this is equal to 1 by the Pythagorean identity. So this is just 1 over cos squared x, which is secant squared, because secant is 1 over cosine. So the derivative of tangent is secant squared x. A quick word of caution. I know as we're memorizing or learning these things, it can be tempting to memorize this as tangent is secant squared. I warn against that language. I would strongly suggest that you remember this as the derivative of tangent is secant squared. Not just because it's not true without that, but also because we're going to eventually go both ways on this derivative ladder. We're going to talk about going, down by taking more derivatives and going up by taking antiderivatives. And if you don't remember that the derivative is attached to this statement, then it can be easy to confuse yourself down the road. So it's not that tangent is secant squared, it's the derivative of tangent is secant squared, and so on. All right, that leaves 2 for you, cosecant and cotangent. I'll tell you cotangent. Because there's a kind of nice interplay here. There's a pattern between the derivatives of the functions and the derivative of their co-functions. So you notice the derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. So if you swap a function for its co-function, you can swap the derivative for its co-derivative. And the only thing you got to remember is that a negative comes along. A negative pops out here. So you know that the derivative of secant is secant tangent. And based on this pattern, you might suspect that the derivative of cosecant is cosecant cotangent, but with a negative. And you'd be correct in doing so. But you're going to prove that. You're going to prove that in your homework by running through the same sort of quotient rule stuff we just did. Questions on these? Okay. I do want to take just a second to look geometrically at sine and cosine. f of x being sine x, meaning f primed of x equals cos x geometrically. And what I mean by that is thinking about their graphs. I'm going to call this 2 pi. I'm going to call this 1. Call this -1. That makes right about here pi. Right about here pi over 2. And then right about here 3 pi over 2. I'm going to start by graphing sine. The sine of 0 is 0. The sine of 1 is pi over 2. The sine of pi, the sine of pi over 2 is 1. The sine of pi is 0. The sine of 3 pi over 2 is -1. And the sine of 2 pi is 0 again. So we expect graph looking, and we get indeed a graph looking something like this for sine. Okay. This is the graph of sine x. So in black here we have sine x. Now if I come in and draw in some tangent lines, up here the tangent line appears to have slope 0. Over here the tangent line appears to have slope 0. Right in here, the tangent line appears to have slope 1. Sorry, -1. Over here, the tangent line appears to have slope +1. And over here, the tangent line appears to have slope +1. So if I just took those tangent slopes and I used those to guess at the graph of the derivative, what sort of graph do I get? Let's do it. Zero, 1 would be on the graph of my derivative, because when x is equal to 0, the slope of the tangent line here appears to be 1. Pi over 2, 0 would be on the graph of my derivative, because when x is pi over 2, the slope of the tangent line is 0. Pi, -1 would be on the graph of my derivative. 3 pi over 2, 0, and 2 pi, +1. So if I just gave you these points and asked you, what do you think this second graph is? I'm pretty sure everybody would tell me cosine, and you'd be correct. What do you know? So that guessing game that we were playing with the derivative graphs last week, you can use that to get, or at least to guess, that the derivative of sine is cosine. It certainly looks like cosine, and it is. It's exactly cosine. We just proved that a second ago. But I wanted to show you the geometric connection here because it is worth going through. Does everybody understand what we're doing here to here? You guys remember playing this game last week? You guess at the slope of the tangent line and then use those to plot points on the graph of the derivative. Right, so my original graph was f of x equals sine x. And just by guessing at the slopes of the point along the original, we were able to get this thing that looks a shitload like cosine, and it's 100% correct. The slope of the tangent line anywhere along sine is the y value along cosine. And vice versa is not quite true, but if you take the derivative of cosine, you get negative sine. So if you take, if you want the slope of cosine here, you would take the sine value there and negate it. So the sine there is 1, sine of pi over 2 is 1. So the slope of this guy right here is negative 1. It's a neat connection between those two things. Your textbook does have this picture drawn a little nicer than I've drawn it. I don't like their proof for the limit there, so I don't do it. But you see here exactly what we did. It's this game. And this looks like cosine because it is cosine, and that's what they prove here, the same way I proved it. Their argument for this limit, I think, is way more complicated than it needs to be. I really prefer my argument for this limit that we went through in class today, because they do theirs based on arc lengths, which are tricky. But then the argument for the second limit follows from the first the same way we did. And you get the derivatives. So the next thing I would like to do is just get a little bit of practice cooking up derivatives of not just trig functions, but functions related to trig functions, functions that involve trig functions. So let's do some of that. Find the equation of the tangent line to f of x equals x squared sine x at x equals pi over 2. The nice thing, we couldn't differentiate this function previously, right? We didn't have the tools we needed because we didn't know how to differentiate the sine part here. But now we do, right? So let's go ahead and do it. I need two things, as always. To find the equation of any line, I need a point on the line, and I need the slope of the line. The point on my line here is pi over 2 comma something. To figure out the something here, I have to know what is f of pi over 2. It's pi over 2 squared times the sine of pi over 2, which is what? What is, so pi over 2 squared, that's pi squared over 4. What's the sine of pi over 2? Help me out with this. What is the sine of pi over 2? Think about your unit circle. Pi over 2 is a quarter of the way around, so that's the north pole. The y value at the north pole is 1. Yeah, so this is just pi squared over 4. Now to find my slope, I need f primed of pi over 2, which I'm going to get by cooking up f primed of x and then plugging in pi over 2. F primed of x is the derivative ddx of x squared times sine of x. And which rule do I need to compute this derivative? Yeah, the product rule. So this will be the derivative of the first, x squared, I'll write it out as x squared primed times sine x plus the first left alone times the derivative of the second, so x times sine x primed. And this way of writing things out in the prime notation before taking derivatives is a great middle step. If you do this, you will make far fewer mistakes on product rule problems. Once you've written it out, then go ahead and take your derivatives. So x squared, his derivative is 2x. This is 2x sine x plus x squared times the derivative of sine x is cos x. So that's f prime, which means f primed of pi over 2, which remember is my slope, is 2 times pi over 2 times the sine of pi over 2 plus pi over 2 squared times the cosine of pi over 2. And you will keep up. So again, I have some pieces that I need to evaluate from my unit circle. What's the cosine of pi over 2? Yeah, cos of pi over 2, this piece here is 0, which means this whole piece goes away. The sine of pi over 2, we said earlier, that's 1. So f primed of pi over 2 is 2 times pi over 2, which is just pi. So this guy is just pi. So now I've got my point and I've got my slope. So our tangent line is y minus y0, which is pi squared over 4, equals m, which is pi, times x minus x0, which is pi over 2. Not too bad, right? So your homework this week is mostly this stuff in the first half. And then in the second half has a lot of chain rule things. Before we go much further, I just want to make sure that we're comfy with this problem, because this is kind of archetypal of the first few problems in the homework set. Just for fun, these aren't easy functions to graph by hand, but just for fun, let me show you the graphs of these together with the tangent line. So f of x is x squared times the sine of x. Kind of a weird looking function. I can rescale my y-axis here. Something like this. And I'm looking for a slope of a tangent. I'm looking for the equation of the tangent line at pi over 2. I claim that that is y minus pi squared over 4 equals pi times x minus pi over 2. What do I do here? X minus pi over 2. And if we come zooming in here, here's the good spot. See if it'll nail pi over 2 for me. Won't quite. My point of tangency is pi over 2 comma pi squared over 4. This is my tangency. So right here at this point, the blue line is indeed tangent to the red graph, right? You all see that? This red graph does all sorts of cool things. But if I want just the tangent line right there, that's what she looks like. And we could do this for any point on this graph. More generally, for any point on any graph that's made up of power functions and trig functions. The last thing we need to be able to do before getting to, masters of differentiation is to differentiate composite functions. That's what the chain rule helps us with. I think maybe it's worthwhile doing one more practice problem involving the product rule and this stuff before we jump into the chain rule. So let's do that. I'll end today with a little discussion of the chain rule, but we'll get into it in earnest on Wednesday. So one more example, just regular trig derivative stuff. Let's let f of theta be theta times sine theta times cos theta, and find just f primed of theta. This is an interesting challenge because there's multiple products in here. Right? This isn't just two functions multiplied, there's three functions multiplied. Any ideas how we could get started here? I would encourage that you think about this as a sort of product rule within a product rule. So we're going to use the product rule twice. F primed of theta, my derivative here, should be, I'll split it up like this. So I'm kind of splitting it up like this as one piece and this as the other piece. So I differentiate the first piece, leaving the second piece alone. And then I add that to what I get by leaving the first piece alone and differentiating the second piece. This is just applying the product rule. But the catch is that within here, I need another product rule. So this will be theta primed times sine theta plus theta times sine theta primed. And all of that is being multiplied by cos theta. And then we're adding that to theta sine theta times cos theta primed, like this. Does everybody see it? Here's your first product rule. Here's your second product rule. Now I can plug in for all of these little derivatives. My variable is theta, so the derivative of theta is just 1. This is 1 times sine theta plus theta times the derivative of sine theta is cos theta. All of that is being multiplied by cos theta. Plus, here I have theta sine theta times the derivative of cos theta, which is negative sine theta. Then we can distribute all of these. So I've got cosine being distributed to this and to this. I'll have sine theta, cos theta, plus theta times cos squared theta, right? Cosine times cosine. And then here, I'll have theta times sine theta times negative sine theta. That's negative theta sine squared theta. And that's your answer. Now, if you're very clever, you can rewrite this using double angle identities, but I would stop here if the problem's just asking you for derivatives. This is good. So this line, you can stop here. But if you want to, sine theta times cos theta, and here I'll write it like this, sine theta times cos theta minus theta times, you can factor out the theta there and you get cos squared theta minus sine squared theta. Both of these you can do some trig identity work with. You know that sine 2 theta is 2 sine theta cos theta. So this piece could be rewritten as 1/2 sine 2 theta, because that is equal to sine theta times cos theta. And on the other side, you know that cosine of 2 theta, double angle for cosine, is cos squared theta minus sine squared theta. So you could rewrite this piece as cos 2 theta. So if you wanted to, you need not do this, but you could. You could rewrite this as 1/2 sine of 2 theta minus theta times the cosine of 2 theta. Just a little bit of practice in using your trig identities. If you're writing all in one color, you may want to tuck this like in a box or somewhere out of the way. It's just neat that both of these end up to be double angle things. That's the only reason I'm showing you that. But this line right here is what I want to make sure everybody can get to. Are there any questions getting up to this line? Alrighty, this is a reasonable place to stop. So before I let you go, I got just a few minutes here to introduce the chain rule. Composite functions are functions made by shoving one function inside of another. For example, the sine of x squared, or e to the tangent x, or the natural log of cos x. You get the idea, the square root of x squared minus 3x plus 7. This sort of stuff. They have an inner function and an outer function. Here, the outer is, I'll call it sine of u, and the inner is u equals x squared. So when you plug the inner into the outer, you get that guy. Here, my outer, I could call it e to the u, and my inner is u equals the tangent of x. You guys help me out here. What's my outer and what's my inner for this one? Outer first. What's the outer function here? Yeah, the natural log, right? So I would say that the outer function here is the natural log of u, and then my inner function is u equals cos x. And then finally this guy, my outer here would be the square root of u, and my inner is u equals that polynomial, x squared minus 3x plus 7. Being able to recognize a function as a composite is important. Just being able to decompose composite functions as inners and outers. The way the chain rule works it's very nicely written in Leibniz notation. It says that if your function is a composite, like y equals f of u of x, then y primed is equal to f primed of u times u primed of x. So you sort of differentiate the outer, leaving the inner alone, and then multiply by the derivative of the inner. In Leibniz notation, this looks very nice. This says that dy dx is equal to df du times du dx. So you can kind of think of the du's as canceling, and you get df dx or dy dx, which is your normal thing. I'll be showing you guys how to do this. We'll go through a basic proof. The proof is not horribly complicated, but it is a little bit of work. And then I'll show you how to cook up the derivatives of all of these things. Now, your homework for this week has some chain rule stuff in it. We're not ready to actually start on that stuff yet. You can take a look and you can try, right? I've given you the formulas here, but I haven't shown you how to do it. So don't feel any pressure to complete the chain rule portion of the homework between now and Wednesday, but please do get in there and work on some of those problems that just have trig functions, or that that don't require the chain rule. I think the way I've set it up is that we got about 20 questions this week, and the first 10 of them you should be able to do now. And of course, this logged me out. All right, we don't need to grind on this. You can do the first half of the homework set now. And the rest of it you can do if you want using this, but for now, just get in there and work the first 5 or 10 problems. Of course, if you haven't caught up, if you still need to do any of last week's homework, please go ahead and submit an extension request. I'll grant those right away. And that is really it from me today. Any burning questions before we leave? Yes, President's Day is, I believe, not an acknowledged holiday for the college. Oh, but but I'm going to be out of town on the 14th. So I'm going to probably have to pre-record some lectures. So yeah, President's Day, not a holiday for the college, but I'm going out of town for Valentine's Day. So I think I'll be pre-recording the lecture for the 15th. I'll have to look and see exactly where that falls. The other thing, and I appreciate you mentioning something here before we go, is that we need to be keeping on top of the student teaching stuff. So let me just get rid of all of this and make sure. Our next student teaching thing, which is coming up here, grade distribution, master student teaching, might not be until after exam 1, but I just want to make sure. So what was the next thing we had signed up for? We got product and quotient, power exponentials, we've already done these. Multi-tones rule, anything before that, 4.1. So this is Kevin's section, I think is going to be, let's see, so linear approximation, that lecture is on the 17th. Is that the next one? Okay. Yeah, so please make sure that you guys contact me and talk with me about these things by the dates that we discussed in your email, right? So it's just been a few days since I've gotten any emails about somebody panicking about their student teaching, which makes me worry that we haven't been staying on top of it. But it looks like the next few folks up at bat here are going to be Kevin and Julio. And I think Julio, yeah, you guys are working together with Chris. So I need Chris and Julio to stay in contact with me. We need to get ready for our little rehearsal. So you guys need to have your materials sorted out by then. I think, Jonathan, I still need to nail this down with you. We had an email exchange. If you could please just check your email and get back to me on that so we can get that nailed down and everything will be good to go. But yeah, we will have class on President's Day, but it may be a pre-recorded lecture because I might not be back into town in time to deliver a live lecture for that. That doesn't look like it'll cause any conflicts with the student teaching, but those of you who have student teaching coming up soon, please send me an email and make sure everything is on the up and up there. Any other questions before we scoot? Alrighty, I'm going to go ahead and end the lecture here. I hope you guys have a lovely rest of your day. Please do get started on that homework. If you need more time on any of the old homeworks, just request an extension. I'll be going in and clearing those in a few minutes. And then if you do want to solve problems, you want to come talk to me about anything, I have an office hour this afternoon from 1 to 2 p.m. All right, take care, guys. And I will see you next time. Oh, the exam, around 15 questions, somewhere around there. There will be a few true false, a few multiple choice, and then the rest will all be free response. I'll talk a lot about the format of the exam as it gets a little bit closer. All right, take care, guys.